grounding and zones of equipotential. We saw that within a zone of equipotential, there is little or no difference in potential between the line and everything in the zone. We also saw that when a lineman is working on a de-energized line within a zone of equipotential and the line becomes energized, current flow through the lineman is limited or eliminated. During this part of the program, we'll watch as a lineman establishes a zone of equipotential for working on a three-phase line. As we go through the example, you should keep in mind that although the procedures you're watching are typical, they may not represent the procedures your company follows. However, the basic principles remain the same. In this example, a crew has been assigned to change out the insulators on this three-phase circuit. It has been decided that the line will be isolated, checked for potential, and then grounded. When the grounds are applied, the line will be considered de-energized. Before isolating the line, the crew members examine the work site and prepare for the job. The crew begins by laying out the grounding equipment and examining it. The grounding equipment is checked to ensure that it is suitable for the job at hand and that it is in sound condition. Next, a temporary ground rod is driven into the earth. The ground rod should be placed far enough away from the butt of the pole so as not to present a tripping or falling hazard. After the temporary ground rod is driven, it is cleaned with a wire brush where the ground lead is to be connected. The clamps on the ground leads are also cleaned with a wire brush to ensure good connections. Then, one end of a long ground lead is connected to the ground rod. For safety reasons, traffic cones are placed next to the temporary ground rod as a visual warning of its location. After these preparations are completed, the line is isolated. In the meantime, a lineman has climbed the pole where the work assignment is to be carried out. After receiving word that the line is isolated, the lineman checks the line for potential. The potential test verifies that the line is isolated, so the lineman knows that it is safe to apply grounds. At this point, the lineman can proceed to apply grounds to establish a zone of equipotential. He begins by attaching a cluster bar around the pole. The cluster bar is positioned about 18 inches above the neutral conductor. This cluster bar has a short grounding jumper permanently connected to it. The other end of this short jumper will be connected to the system neutral. Before any ground connections are made, the lineman uses a wire brush to clean the neutral conductor to ensure a low resistance connection. Once the neutral is clean, he connects the cluster bar's short lead to the system neutral. A wire brush is then used to clean the cluster bar to ensure low resistance connections. In the meantime, a crew member on the ground ties a rope sling to the long ground lead about 3 feet from the clamp. The long ground lead is sent up on the hand line, and the lineman ties the rope sling to the cluster bar. Doing this relieves the strain of the weight of the conductor from the ground clamp and the ground lead connection. Next, the lineman takes the clamp and connects it to the cluster bar. He then tightens the connection. Once this is done, another ground lead is sent up to the lineman. Both of the clamps on the lead were loosened before the lead was sent up on the hand line. The lineman takes the lead and connects both of the lead's clamps on the cluster bar. One clamp is tightened facing down, and the other is tightened facing up. This lead will be connected to the center phase conductor. The lineman then uses a wire brush attached to the end of a universal stick to clean all the phase conductors. Once the phase conductors are clean, the lineman takes a shotgun stick and engages the ground clamp that is facing up on the cluster bar. He loosens the clamp and lifts the clamp from the cluster bar. The lineman raises the shotgun stick with the ground clamp until the clamp is above the center phase. Then, in one motion, the lineman applies the ground connection to the center phase and tightens the connection. At this point, the connection from the cluster bar to the center phase is complete. The lineman uses another ground lead to connect the center phase to one of the outside phases. And finally, another ground lead is used to connect the center phase to the remaining outside phase. A zone of equipotential has now been established. In other words, the difference in potential between the line and any point within the zone has been limited or eliminated. This way, current flow within the zone is limited or eliminated. As long as the lineman stays within the zone of equipotential, there will be little or no difference in potential between his body and the line being worked on. If the line should become energized while the lineman is in contact with the line, there will be little or no current flow through the lineman's body. In this part of the program, we watched as a zone of equipotential was established on a three-phase line. Before that, we used Ohm's law to demonstrate current flow in an energized line. We also looked at how equipotential grounding works. Specifically, we saw that equipotential grounding limits the difference in potential between you and the line being worked on. This way, if the line becomes energized, you won't be a path for current flow. We began the program by going over ways in which an isolated and de-energized line can become energized. And we looked at a typical grounding procedure in which grounds are established on both sides of a work area. The grounding examples we looked at here aren't the only types of work areas you'll encounter, but you should be able to apply the information we've covered here to any overhead line maintenance job. Remember, the high voltages and fault currents possible when you're working on overhead lines make proper grounding a vital concern for you.